All right. We have gone through many components and we have seen examples. I'm going to do one last example, something we have seen several times, independent and is part of some other thing and all that. But then I'm going to do the simulation and test bench and everything, so we see a few things about that. So let's get started with that, and that is a maximum finder circuit. And I look at it as a case study. It's really a very small example. The circuit is maximum finder. I'm using remember the comparator, that the cascadable comparator. I'm using that. And that cascadable comparator has three outputs. I don't really need the three outputs. And uh, just a simple comparator that would do the greater than would be useful. But this is the harder. When I'm writing the Verilog description of it, I'll do it in various ways. And I'm just showing you one suggested way of doing the hardware using the existing components we have had. A and B are 4 bits, and so this is 4, this is 4, and if A is greater than B, this becomes 1, and if this becomes 1, the A input goes into the output, and if the output is 0, that means A is not greater than B, then B is going to go to the output. Okay, so that's how it works. And this is the comparator. And remember, if I want the equal output to become 1 when they are equal, I have to put 0, 1, 0 on the output, on the input, LEG inputs. But then I'm not using the output EQ anyway. That's one way of writing it. A and B are 4-bit inputs, and W is a 4-bit output. I'm using assign statement, okay? And I'm using an assign statement for two assign statements. Here I'm showing you that I'm showing you that you can write two assigned statements. You can order them however you want, and it still works. The first assigned statement says GT equal. If A is greater than B, then 1, otherwise 0. So I have a wire called GT, and I'm using GT as the condition for the next condition operator that comes on line 4, which says that if GT is 1, take A, otherwise take B. Okay, this works. This is fine. You don't like this order, you want to put this on top of this, that's fine. But then I can also show you writing Verilog description using always the statement. Now, Verilog, as I have said many times, is a very forgiving language. Sometimes forgiveness is not good. Here, I did not declare GT. I did not say anything about GT. Fine. Verilog says, well, I can do it for you, and it declares it for me, and so I'm safe. On the other hand, if GT was here is a scalar, a 1-bit thing. If it was a 4-bit thing, then Verilog would declare it for me as a 1-bit thing, and then I would get into trouble. So don't use the forgiveness of Verilog. Declare everything yourself. Don't let it declare things for you. And therefore, here I say wire GT. Okay? And again, this is good. This works without that. But line 2, having wire GT would be just making sure that you don't depend on Verilog making decisions for you. Well, I can write this in a different format also, or a different form. I can do this. Just know that we have learned always. I can say always at A and B are the inputs. Okay. Then you say if A is greater than B, W equal A, else W equal B. Okay? Since this is one statement, I don't have to put begin end. Okay? I can if I want. Everything in the sensitivity list, everything that is being looked at, they have to be in the sensitivity list, and therefore A and B are in the sensitivity list. I want to make sure W receives an output, a value no matter what. Well, the thing is, A is either greater than B or not greater than B, and therefore W is going to receive a value anyway. And therefore, I could skip begin and end. But then, if I want to look at that rule religiously, then I say, well, no matter what, I have to make sure W gets 8. It's not 8, it's 4. Tick B is 0. And in that case, since now I have one statement here, another statement here, my begin and end would be mandatory. If I do this, I would have to put a reg, not here, here, because W is now left-hand side in an always statement. Okay, how else I can write this? I can write this as simple as this. Okay, let me use a different color. Assign W equal, if A is greater than B, then A, otherwise B. Okay. Or you want to do the hard way. If you have a comparator, you want to instantiate that. If you have a multiplexer, you want to instantiate that. You can do that as well. And if you like to do gate level, you can do that. Okay. Let me see what else is worth saying about this description. Nothing really. I've already shown you 3 ways of doing it: this, this, and this. Let's put it in a test bench and test it. Okay, in order to put it in a test bench, I instantiate the component. Remember, the component is input. Let me write this down here. Max Finder. Max Finder. The module is input 3:0 A, B, output 3:0 W. Okay. I want to give value to the inputs, and then I want to observe the output. The inputs I declare as AA and BB. AA and BB. In order to be able to assign values to them, I use initial statement. An initial statement, if there is something on the left-hand side in an initial statement, it must be declared as reg, the same way as the always statement. And since I want to use AA and BB, that I want to connect to A and B inside an always inside an initial statement, therefore I declare them as reg. I declare them as reg on line 3 and 4, and I give them values. 4 tick B0. This one I've used 8 tick B0. Verilog is very forgiving, and it forgives me for doing this. Actually, what it does is that it creates 8 bits and then truncates 4 bits. If you do something like this in VHDL is not going to let you get away with it that easily. Then I want to observe WW, which I'm going to connect to W. Then the next line, line 7, I'm instantiating the component and I'm wiring AA to A, BB to B, WW to W. Alternatively, instead of doing the connections by ordered connection, I could do named connection. Named connection goes like this. It says the component name AA, that was little a, for no, that was capital A. The component port A connects to the component A connects to my local AA signal. And then I don't have to order them. B of the component connects to BB signal. And then it says W of the component is this W lowercase, connects to WW. Okay, so instead of this, I could do this. Okay, this is called ordered connection. This is called named connection. Okay. And then that's it. That's it. You remember in test benches do not have ports. Test benches have everything that is input to the component you are testing that you want to use inside an initial statement or on the left hand side in an always statement. Set them to give them the declaration reg. Okay, if you want to set initial value, you can do that when you are declaring the reg. Anytime you want to observe, declare it as wire, like WW in this case. Let me go through the initial statement. Wait 20 nanoseconds. While you are waiting, AA is all zeros, BB is all zeros. And then in 20 nanoseconds, AA changes, BB changes. 20 nanoseconds later, both of them change again. 20 nanoseconds later, AA changes, BB changes. But then there may be propagation delay and all that, so I don't stop immediately. I wait 120 nanoseconds and then stop. It's always good to have a stop in an initial statement. Even though when it reaches the end, it stops anyway. But then it's a good thing you can tell that, okay, I'm stopping here. And this is the test bench. There are a lot of things I could do. I could do this. Let me show you. I could say repeat 11 times maybe. And then each time wait 29 nanoseconds. I like prime numbers. 29 nanoseconds. And then AA gets dollar random. Okay, so when it reaches this statement, keeps B the same, but then it puts every 29 nanoseconds for 11 times, it puts a random number on AA. All right, as we go through, we will show you more test bench techniques. This is the simulation, and you are seeing that in all cases, let's show that using yellow. In all cases, the grader of A and B appears on the output. The grader of A and B appears on the output. Okay, here A is still this, and therefore the grader of A and B appears on the output. Here both of them are at the end, both of them are 0, so 0 appears on the output. All right, we have covered components, we have covered simulation, and I will add one more lecture to this and then go over some of the Verilog constructs. Okay, that's good for now. Thanks.